Okay, our third example here is looking at solving quadratics that are differences of squares. So again, differences of squares requires that we have two perfect squares and they are subtracting. So our first term in example A is pretty easy to spot. So we talk about the square root of 9 is 3, the square root of x is, or x squared is x. The square root of 0.64 is actually 0.8. Okay, because 64 is, the square root of 64 is 8, and then we've got some decimal relationships there. Okay, and the square root of y. So we can do it that way. Alternately, if you didn't spot that right away, you could have done it how we did before dealing with decimals. You could have factored out a 0.1 and then left it as 90, but now that's not a perfect square. Okay, so that's not really a very good option. This way is better. So 64, spotted as a perfect square. If you're not 100%, you will have access to your calculator if you're dealing with a decimal like that. So please go ahead and use it. Second one, just because it's in the denominator doesn't mean it's not a perfect square. So in this case, we're dealing with x over 3 as our first term in both brackets. We're dealing with 2 over 5 as our second term in both brackets. It's just opposite signs. And that's it. That's all I have to do. Ta-da! Okay. So when we get to C, same principles apply. D, same principles apply. We're just doing a little bit of both. Now we're taking those first steps of dealing with perfect squares and also dealing with binomials within polynomials. So this is a perfect square. So I'm going to use square brackets around this. And I've got 2x minus 1 and 2x minus 1. My square root over here is y plus 4. And then I just do opposite signs. But I'm not done here because I can collect like terms within brackets. Don't forget your equal sign out in front. Okay, don't have like a running line of a bunch of equal signs. Don't do that. Bad. Not real math sentences if we do that. Okay, so then this first set of brackets, I've got 2x, no other x terms, so that stays the same. Minus 1 plus 4 is going to be positive 3. But before I do that, I'm going to write my other variable as well. My second set of terms, this negative actually applies into the brackets. The positive applied here, but it doesn't change any signs. So I've got, again, 2x. This time I'm subtracting y though, and I've got 1 minus 4 is negative 5. So that would be my final answer. I would have to try to collect as many like terms as possible. Last, or second last one? Second last one? Yeah, almost there, guys. Okay, same properties still apply. If you need to substitute in and think like that first, call this R and Q or something, go ahead. Actually, I'll do that for this one. So I've got 3R plus and minus 2Q and 2Q. But because this is happening so quickly and the difference of squares factors come pretty easily, I don't usually like to do that step just because it's just an extra step. But if you need to, go ahead. 3 times 2t plus 1, so plugging back in for r, plus 2, s minus 2 is in for q, And then we've got 3 2t plus 1 minus 2 times s minus 2. Okay, so make sure you're plugging them in back correctly. Don't lose those coefficients out in front. 2 is still there, 2 is still here, 3's are still there. Okay, always double check that we're not dropping anything. Opposite signs still happen. Okay, we're going to expand from here. 6t plus 3 plus 2s minus 4. 6t plus 3 minus 2s plus 4. Okay, and notice how my signs are different on those second term or those later terms because of that difference in sign within my binomials. Last step, collect like terms within the brackets. So I've got 6t plus 2s minus 1 and 6t minus 2s, and that's plus 3 and plus 4 is plus 7. Okay, so only collect terms within brackets. Okay. Last one. Almost there. We're so close. Well, 32 and 18 are not perfect squares. Crap, what are we supposed to do? Oh wait, that's not the first step actually. My first step, if I go way back up here, is, oh, it's way back here. Greatest common factor. So, if it doesn't look like a perfect square exactly, but we got where we've got a binomial with otherwise squared pieces and they're subtracting, well, maybe we can turn this into a difference of squares. So we can take out a 2 from both of those. And we're left with 16x plus 2 squared minus 9, 2y minus 3 squared. From there, well, 16 is a perfect square, x plus 2 squared is a perfect square, 9 is a perfect square, so is this piece here, 2y minus 3 squared. So I'm dealing with a difference of squares. So let's go ahead and break this down a little further. This leaves me with 4x plus 2. As my square root of my first term. The square root of my second term is going to be 3 times 2y minus 3. Okay, and then just opposite signs. I'm going to distribute and collect like terms. So again, I'm going to skip that actual writing out of that step because it's going to take up the whole width of my screen. Okay, so 4x, no other x terms in that bracket, so I'm just going to have 4x. We've got 8 minus 9 is minus 1, but I like my variables all together, so it's going to be 6y first. Second set, 4x minus 6y, because of that negative out front here. And then 8 plus 9 is going to be 17. Okay, and I am done here. Now, you might be like, but 4 and 6 have a common factor, Miss Conrad. Like, did we miss something? No, we didn't, because the third term doesn't have a common factor with the other two. So we can't take it out of just 2 of the 3 terms. It would need to come out of all 3. So we are, in fact, done. So there's lots of practice questions for you to try. You want to ace factoring. Like I said, we're going to see it a number of times in assessments. And if you can't factor like 75% or higher, you probably shouldn't be taking grade 12 pre-cal. So we want to master this. So practice, practice, practice. And tomorrow you'll be able to ask some questions in class.